Continue. So here we show this band diagram as the flat band condition where the gate voltage is 0. And then here, this MOS structure, we have the flat band. So the EF in the metal is the same as the EF in the silicon. And the distance between the EI and the EF is defined as a phi b, or let's say Q phi b if we think about the energy distance. So let's look at the positive voltage where you bend down the band like this. So here the blue curve is the band diagram when we have the positive voltage. So everything is bent down, but the relative distance, will keep the same, okay? Because the band gap will not change. Like if you have EG for the band gap, so at the surface, the band gap will be the same at the bulk. So here we want to define one concept, that is, let's say to the very deep substrate, we call this side as a bulk of the substrate. So to the bulk of the substrate, then everything is still flat, because here the electric field cannot penetrate too deep into the substrate. So in the substrate is still like flat band. So only the surface will change. So here the positive voltage basically bend down the band of the surface, and we have this surface potential defined as a bending of the surface band edge EC. So this is defined as the phi s. So this is defined as a phi s. So we bend down the band edge by phi s. If you compare the blue curve and the red curve to start with, then you see the band edge is bent down by this phi s, and we call this surface potential. Actually, it's Q phi s if we talk about the energy distance. So this phi s is important. We're going to derive that in the next slide. Oh, I think one more slide before that. So here is the charge distribution of the MOS structure in those different conditions. First is the accumulation. This is when the gate voltage is negative. So then we push up the band. So negative voltage, negative voltage is going to introduce negative charge. So here this is a charge distribution. So negative voltage will introduce negative charge to the gate. And we said that in the substrate, the surface will be accumulated with the holes. So those holes will balance the negative charge to the gate. And then when the gate voltage is larger than 0, but let's say smaller than the threshold voltage, then we bend down a little bit. Then this is the depletion, because we have a little bit positive charge to the gate by the positive voltage. This positive voltage will push away the holes. Then what is left is this Na minus. This is the nucleus of the acceptors, which is negative charged. But when we have the strong inversion, right, when the gate voltage is large enough, larger than threshold, then we are going to induce the surface electron. This is the inversion. Because you have so many positive charge here, then you need additional electron at the surface to balance that. But here the principle is that for a capacitor structure, for those two plates, no matter what, the charge will be balanced. So that's why here the Q total on the metal gate, which is here, will be the same as Q total in the substrate, in the silicon surface. And in this strong inversion condition, then we have two components for the negative charge. One is this depleted acceptors, this Na minus, and then the other is this inversion electrons to the surface. But before the strong inversion, let's say in the depletion, then the negative charge will only be this depleted acceptors. All right, any questions? Okay, so let's do some derivation of the threshold voltage. This is an important parameter that we want to derive for the MOS structure. So basically, the threshold voltage is the gate voltage where the MOS is under this strong condition, a strong inversion condition. So we want to know what is the voltage. And to derive that, let's look at this diagram here, where we show the charge density along the MOS direction, and then the electric field, and then the voltage potential. So here, let's look at the charge density first. This is what we discussed from the previous slide. This is the depletion, so we don't have the surface electrons yet. So we only have this Na minus, so that's why we draw it in the negative part. So this is the same as this one, this Na minus. So here we have the doping density Na, so the charge density will be Q times Na, and then we have the W, which is depletion width W. So the total charge here, Q total, essentially is the area of this part. So it's QNA times W. So that's the total charge, total negative charge caused by this depleted acceptor. And then we want to do one integration of the charge here over the distance, let's say the W. And then you will get the electrical field. Why is that? If you recall your college physics, I suppose you have learned the Gauss's law in the electromagnetics. So basically it says that the charge, if you integrate the charge over some volume, or in this one-dimensional case, over this distance, you will get the electrical field. And here, since we assume the charge doping is a constant, so it's let's say a constant value here, when you do the integration once, a constant function will become a linear function. Let's say zero order will become first order. So that's why here the electrical field is a straight line. And you can calculate what is the ES here, which is the electric field at the surface of the silicon. This is ES. And that is the Q total divided by the epsilon of the silicon. So epsilon 0 is the permittivity of the vacuum, and then the epsilon silicon is the relative permittivity, or the dielectric constant. So this is the ES, is the Q total divided by the epsilon. This is from the Gauss's law. Gauss. So this is the ES. So basically, the constant function becomes a linear function. And then we do one more integration from the electric field to the voltage potential. This is by definition, the electric field along some distance will give you the electric potential. So let's say if you do the integration of the electric field along this W, then you will get the voltage potential. And you know this is a straight line, that means linear function. A linear function will become second order parabolic function if you do the integration. So that's why here this is a parabolic second order function here. Or in other words, the potential here will be proportional to the square of the W, because because it's a second order function from the first order linear function. And also, if you think about the integration from the linear function to the second order function, like x, if you do the integration of x, then x will become 1/2 x squared. So that's why you have the half here. And here the x is w. We integrate along the distance w. So that's why the surface potential is this one. Integrate from here to the w. So we will get this equation for the phi s. So that is the surface potential. That is the voltage on the surface of the silicon. And we call this phi s. And phi s is given by this formula. Basically, you do integration once from here to here. This is integration. This is the first integration from the charge to electric field. And then this is second integration. And the phi s, okay, is a voltage potential at the surface of the silicon. But you apply the gate voltage, Vg. So if you look at this structure, you apply voltage to the metal gate, eventually the voltage will decay to 0 when you go to the right-hand side. So this is the voltage drop across the oxide and then the depletion region. In other words, the Vg has two components. The first one is voltage across oxide, and we call it Vox. And then the second is the phi s. That is the voltage across this depletion region. So that's why here you see we have this Vg you apply it to the gate, metal gate, and it will first drop across the oxide as a Vox, and then the phi s. Oops. So in other words, Vg, oops, and that. My pen doesn't work. Okay, let me close this. Wait one more time. Any questions here? So here the Vg still doesn't work. The gate voltage dropped across the oxide and the depletion region. So the oxide has a Vox and the depletion has a phi s. So Vg, okay, it works. Alright. So any questions so far? Okay, then let's move on. We are halfway through. So this phi s equals to this equation, which is from here. So basically, it has a dependency on the w. So we can back calculate the w as a function of the phi s. So we move the other terms to the other side, and then we take the square root. So we can get the w as a function of the phi s. So it's this one. Square root of 2 epsilon 0 epsilon silicon phi s divided by QA. And then this Vg, as we just discussed, it has two components. One is Vox, the other one is phi s. So Vox is the voltage across the oxide. So then we can think about the capacitor structure here. We have the charge, positive charge, on the metal, and then we have the Na minus in the depletion region. So no matter what, this is the Q total. The other side will give you the other Q total. So the positive Q total will be the same as the negative Q total. And this is a capacitor structure. And you know, if we define the capacitance, COX, oxide capacitance per unit area, then the Q total will be the capacitance Q times the voltage across this oxide, VOX. And this COX, what is COX? Is the capacitance per unit area of the gate oxide. And by definition, for the plate capacitor, you know the capacitance per unit area, if you have some area of the capacitor, then it's epsilon 0, epsilon oxide divided by DOX. That is the thickness of the oxide. So this is the definition of the plate capacitor. Okay, so here what we want to do is to get the VOX, and then VOX will be this Q total divided by COX. Then what is Q total? Q total will be this area, right, of this negative charge. So that is QNAW. So if we plug in this QNAW to here, then you will get the QNAW divided by COX. That is this VOX. And then plus phi s. And we just calculate the W here. So we can plug in the W. And eventually we get this one. So here this Vg equals to this term plus phi s. So eventually we want to derive the relationship between the gate voltage Vg and the phi s. That is the surface potential. If you come back to here, so we want to quantitatively derive the relationship between the gate voltage and the phi s. You know, when you further increase the voltage, gate voltage, you will have more voltage drop on the silicon depletion region. But we want to have a quantitative relationship. Let's say if the gate voltage is given, then one want to know what is the phi s. So this is the relationship between the phi s and the Vg. And now we want to plug in the threshold condition, which we said is a strong inversion. Phi s equals to 2 phi b. So we want to plug in the 2 phi b. And if we recall what is phi b, we discussed that before. Phi b is here, the distance between the Fermi level and the intrinsic Fermi level. So we said that at the threshold, you need to bend down the phi s by 2 phi b. So that's why we plug in the 2 phi b here. So if you plug in 2 phi b here, then you will get the eventual threshold voltage equation, because here the threshold is defined as the gate voltage when the phi s equals to 2 phi b. So you plug in 2 phi b here, then you get this equation. So this is for the threshold voltage. This is what we want to eventually derive. And also, we want to say that at the threshold voltage, then the depletion width will reach the maximum. So the depletion width will become this one. Basically, we plug in the phi s to be 2 phi b. And the maximum depletion width will be this one. I know the derivation is a little bit tedious, so I don't require the details of this derivation. So what you need to know is the eventual conclusion here, this one, and also know the principle here. So let's say if you integrate charge, you get the electric field. You integrate electric field, you get the voltage potential. Any questions? All right, this is just a summary of what we have discussed in the previous 2 slides. This is copied from the textbook. And here I think in the textbook we have the VFB, the flat band voltage, but let's skip that for now. So we assume that at flat band, the voltage is already, let's say the Fermi level is already aligned. So the VFB can be 0. So this is the threshold voltage definition. Then you can see here, it depends on what? Depends on mostly on the doping, the Na. Why is that? Because the phi B also depends on Na. Then if you want to recall the phi B's equation here, phi B is this natural log Na over the Ni. Ni is a constant at room temperature. It's 10 to the power 10. So mostly this threshold voltage is determined by the Na, the doping density. And you can draw the conclusion that with higher doping density, then your threshold voltage will be higher. And I think you will have one homework on this equation for practice. You plug in the values for those Na and then epsilon and the oxide capacitance. Then you get the threshold voltage. Okay, so this is at threshold voltage. Then above the threshold voltage, if you further increase the gate voltage, then we're going to induce more and more free electrons at the surface. Then according to the capacitor model, the free carrier, in this case, the inverted electron Q inversion, is the oxide capacitance times the voltage. But this gate voltage needs to overcome the threshold voltage to make the inversion. So you need to pay additional voltage. So that's why it's Vg minus Vt. Because at the threshold voltage, then the Q inversion is almost 0. All right, any questions? Let's stop this.